Just going to go through the linear regression PowerPoint to explain the basis of linear regression. This is a statistical process where we are looking at estimating relationships among variables, and in most cases regression analysis is used to help understand how a general value of a dependent variable changes when a single independent variable is varied and all other independent variables are remained fixed. This is called simple linear regression. To establish a meaningful relationship, a model of the data, it is important that only one independent variable is varied at a time, and this relationship or model is found as a function of the independent variables and is called the regression function or the regression model. Using this function, regression analysis estimates the conditional expectation of the dependent variable given the independent variable. And for the purpose of this model, you can imagine regression analysis to refer to a technique to estimate the value of dependent variables which are continuous. So it's one of the most studied types of regression analysis, and we're just discussing linear regression in this presentation. Linear models are generally used for predicting values of y given values of x. However, they can also be used to determine the strength of the relationship between x and y and which values of x or which independent variables should be left out of the model, and that's if we were looking at increasing the number of independent variables. The general form of a linear model is shown below. In the second line, the response y has been replaced by the expectation. This is read as the conditional expectation of y given fixed values of x. So here we have, at the top is the model, this is our response variable, and the betas, we've got beta 1 up to beta p, these are taken as coefficients of the independent variables. In order for our data to be successfully modelled by linear regression, certain assumptions must be made about the data. These assumptions are the general characteristics of the data which are necessary in order to process a linear regression. We've got m predictors, and the response variables observed are each of n cases. So we have an independence of error. This assumes that the errors associated with each measurement or data point of the dependent variable are not correlated and therefore are random. Constant variance, or called homoscedasticity. This implies the conditional variance of the response given the predictors are constant. So what we're saying here is that our variance here is constant and our expected value of variance is based around 0. So the variability of the residuals must fit a normal distribution. In R, there are many ways to import data, so this is just reminding you one of the ways that you can use. So if you were in R, you can go into import dataset and say from a text file, and then this is one of the easiest ways you can import a spreadsheet that has been saved as a CSV file. We've covered this in other modules. If you need to, you can adjust the options of the import wizard because this allows you to look at the data. So this import wizard will actually show you the name of the data set here. In this case we're just calling it crop yield, doesn't matter, and we've ticked here that we've got a heading, and that shows us that the heading here will actually come in to our data frame. What you'll notice here is we've got crop 1 underscore yield and crop 2 underscore yield. There's no spaces in those headings, and that's important because when we bring in the values we will only have 2 variables over here. So you need to tick that you have got a heading and that you're separated by commas because it's a comma separated value, okay, and it will bring it in as 2 columns. Following are some of the functions you'll need to be able to familiarise yourself with calculating some regressions. Whoops. First, we must plot the data sets of interest. Let's say we've got a data set of, say, 2 variables, forest and height. So height was a dependent or response variable, and to plot this you would type into your source file plot forest height, and if this appears to be a linear model you can put model 1 equals lm forest height. So you can first of all have a plot of it, have a look, and if you think it is a linear model you can then name the model and then you'd say model and assign or equals linear model forest height. And when it's been fitted, you can obtain a summary of the model to observe the output. So you just say summary of that model that we previously named. So that gives you the relationship and plots it for you. So when the summary command is used, you will also get, here we can see, we've said crop 1 is that, crop 2 is that. Here's our crop model. In this case we're talking about two crops, we're seeing if they're related. Our data's crop yield. And when we do summary crop mod, we get a linear function out, and that tells you that it's crop 2 is a function of crop 1, and the data is crop yield. It gives you residuals, and it gives you coefficients, and it gives you a significance, and it gives you quite a few other things which we'll discuss as you go through this module. The variables which are called to create the model are shown under the heading call, and then we have a summary of residuals in all the quartiles, and these are displayed along with the minimum and maximum values. It is necessary to see that the residuals are normally distributed, that the mean is close to 0, and the quartiles either side of the mean, Q1 and Q3, have roughly the same magnitude. Then we have the heading coefficients. This is the estimate for the intercept and the slope, and are given along with their respective standard errors. The residual standard error is an estimate of the parameter. The R-squared coefficient is a statistical measure of how well the regression line approximates the real data points. The adjusted R-squared is the same thing, but adjusts for the complexity of the model, the number of parameters in the model. We'll go through these in further detail. Understanding the output. The t-value shown for both the slope and the intercept is the estimate provided for that coefficient divided by the standard error, and the p-value for this probability of achieving a value of t as large or larger than the one shown in the null hypothesis. And in fact the null hypothesis that all the coefficients are 0, which means you have a 0 slope and a 0 intercept. Usually this will be quite small. If the p-value is small, and this means less than 0.05, it demonstrates your model is sufficient, and it is now logical to add a regression line to see how closely it fits your data. We then run an ANOVA for regression, and this is analysis of variance. It provides a statistical test of whether or not the means of several groups are equal, and most of our ANOVA data can be found in the summary command, where we go ANOVA LM1, and in this brackets here is the name of the model that we want to extract the ANOVA from. So most of the ANOVA data can be found in the summary command. However, the ANOVA command can be used for a complete ANOVA table. If your model was called LM1, the command would be ANOVA LM1. And when you do that, you get the analysis of variance table printed out nicely in R, and it gives you the response variable here. This is just one from another example. Here we were looking at sharks and their length and their jaw width. So it gives us the residuals here. It gives us the fit or the residual and the response variable as a function of shark length. Degrees of freedom for regression is 1, and we look over here to the F value and see the probability is very low, so that this is a significant regression. To obtain the residuals of a model, we can actually just ask for the residuals of the LM1. So in this case we've renamed something, or we've got an object here that we're naming residuals underscore LM1, and to get those we just ask for residuals here of that model LM1, and this produces an array called residuals LM1, which contains all the data of the residuals from LM1, and we can then use this to plot against your X values. So we can also find confidence intervals, which is a confit open brackets close brackets command, to see if, and here we get the confidence intervals for the intercept and confidence intervals for the slope, and we get the 2.5% and the 97.5% confidence interval. So that's in fact the 95% confidence interval, which, if we recall, means that if you repeated this study many times, this is where the estimates of the coefficients would lie, 95